Like it's not getting any more. And then, oh, discharge. How exciting. Okay. Oh shit, wrong one. This one. Okay. So what we're doing today is capacitors. Right? We're learning about what capacitors are and how they function. And then we're going to learn an incredibly specific type of problem about capacitors. Now those of you who finished your exam, you get to enjoy this content. Those of you who have your exam on Friday, you don't get to enjoy this content because it's not being assessed on Friday and you're going to be stressing out about the stuff you got on Friday. So those of you who are like, oh, I have my exam early, well, now you get to relax early, right? You chill it out, you're just having a time. Especially because this is probably the easiest lesson we'll ever do. It's really fun, it's really chill. So we're going to understand what a capacitor is. We're going to be capable of solving a very specific type of capacitance problem. Now, I wrote these lectures when my computer broke, so the pictures are shitter now. Solders. Anyway. Do I have? I totally have a, yes I do. So, we're going to be doing as usual. First of all, change the color. I think yellow was the best color. We're going to be, of course, going to ecopol.au, and we're going to be using the code PhysicsGang. Right, and that's going to be our little plug-in doodad. And I want you to look at this. All right, we've got two parallel plates, like these two. Right, they could be square, they could be circular. The shape doesn't exactly matter. I'll put them facing everyone again. We've got these two parallel plates and a battery. In this case, it's a Van de Graaff generator, but it's some form of voltage device, something that has some kind of a voltage. And what that's going to do is, of course, this is going to push positive charges out of the positive end, and it's going to push negative charges out of the negative end. Right? And so what happens, just like in this case, right, when we have our voltage connected to two parallel plates, the positive charges, of course, the positive charges are moving along this wire and they start to accumulate on the, what we would now call, positive plate. And the negative charges do the opposite. They accumulate on the negative plate. Because this battery, this voltage, this potential difference, is inducing a charge separation. It's causing the charges on one side to go to one end and on one side to go to the other end. And it's charging the capacitor. That's what's happening here. So as an example, we have two initially neutral electric plates. And if I turn on the battery, what we see, by virtue of the fact that these strings are moving, which tells us that there's charge on one of these plates, that the charge on the plates is increasing. And I can discharge them, like I'm connecting the two plates. That's actually what I'm doing when I do this. I connect the two plates, except maybe I could do it with this instead, right? I could discharge it. There we go. Discharge, and then it's charging, and then we discharge, and then it's charging. And I want to ask you a question. Right? It's charging because of the battery, and we got all this positive charge on one side and all this negative charge on the other side. When does it stop? When is it done charging? That is the question. That's the ecopol question. When do we stop having positive charges go this way and stop having negative charges go this way? When does it stop? Remember, we're on ecopol.au, and then the utility, the code is PhysicsGang. When does it stop? Alright, we'll start when we have like 7 responses, because that's half. So what do you think? When does it stop? When does it stop charging? When do the positive charges stop accumulating on the positive plate? When do the negative charges stop accumulating on the negative plate? You can write, I don't know, if you want. That'd be nice, just so I know people are paying attention. That's what I do this for. I do this for engagement. I do this for dopamine. Alright? It's not about your learning, it's about me, how I feel. That's not true, by the way. Just for those of you watching the videos at home. All right, 4. Let's get to 5. All right. Oh! It broke! Yay!
Too many responses.
Yeah, too many... God damn it. Okay, hang on. We'll keep our indentations. We'll start it again. We'll try again. Recover. No, cancel. Start. Great. Alright. Life is hard. So, I like how as soon as I harassed you all to fill in the Echo Poll crashed. Really appreciate that. So while we load it up again, I want you to think, when is it going to stop? Anyone got a guess? Anyone want to yell it out?
When the charge or the voltage across the plate is equal to the voltage of the battery.
That is correct. The charge stops when the two objects are in voltage equilibrium. When the voltage across the battery is equal to... I have to sign in! Wait for me. But yes, it's when they're in the same voltage. Oh, what's my password? It was something stupid. Oh, I remembered. I'm the goat. It's not my normal password. It's something insanely stupid. All right. Recover. No! Okay. We're back, maybe? Can someone try it and tell me if we're back? We'll go to previous page. And if anyone can try Echo Poll, tell me if we're back. Just give me a scram. Are we back? We think so? Yay! Yeah, we got responses. I appreciate you. Yes. So this charging ceases to occur when the voltage across those parallel plates is equal to the voltage being provided. And that should hopefully make more sense. As you increase the voltage you are supplying, then you should be able to push more charges, right? Because what's going to happen is as we get more and more charges on this positive end and on this negative end, it becomes harder and harder to take another positive charge and push it there because you're fighting the repulsion. The positive plate is repelling positive charges, and it will stop receiving positive charges when it pushes back exactly as hard as the battery is pushing forward. So when they achieve voltage equilibrium, thank you. Sorry, I'm down with the sickness still. When they achieve voltage equilibrium, the charging stops, right? And when it achieves voltage equilibrium depends on some property of this capacitor, right? Because you can imagine if I had a different capacitor, like maybe this one, which is two things, maybe it could achieve a different voltage. We don't know, right? Or maybe, sorry, it will achieve the same voltage with the same voltage source, but a different amount of charge. So the first thing we need to know, and this is generally true. Is the mic on? Yeah, it is. I hope people in the recording can hear this. They probably can, right? Two circuit objects. In our case, it's going to be capacitors, but this is just generally true of things that can redistribute charge, right? Will attempt to reach a voltage equilibrium if they are placed in parallel, all right? Now, once this is reached, they are in there. Oh, is this not on the whole time? It ran out of battery. Okay. Gosh, yeah, okay, it's out of battery. I'm so sorry, online besties. You missed nothing. I was rambling. So we got to take this. I can't believe who just no one charges this shit, man. All right, we'll do this one. I'm so molding. I'm tilted. Does this work? All right, good. All right, online gang, I got you. Even though, why would you watch these? Watch the web streams, they're better. All right, anyway, if you plug two doodads in, right, this one and that one, right, they will reach voltage equilibrium. That's what they'll try and do. Now, You might think, hey, Tom, was that a battery or a capacitor? Well, the symbol for a battery is a freaking capacitor. Because we treat them like the same sort of thing. It's a thingy that induces a charge separation. It's just that we make it a little easier for you to tell which end's a positive, which end's a negative. All right? But that's why it's parallel plate, right? Because it behaves analogously to a capacitor in this voltage equilibrium circumstance. You didn't need to know that. Don't worry. If that confuses you, just forget it. Now, of course, when you immediately plug something in, it trends towards voltage equilibrium. It does not immediately achieve it, right? But we will assume, or we will only ever deal with, not working computer, we will only ever deal with things in their steady state, right? Things that have already reached their voltage equilibrium, all right? We assume every single step you take takes 10 trillion years, and therefore the steady state is always reached, right? Because obviously in real life, if I were to charge this capacitor, it takes time, right? It's charging. Discharging. Cool. There we go. Right? But in this course, we're going to assume everything's steady state, all right? If you do actual electrical signal analysis, of course, you do transient behavior. And capacitors have very interesting transient behavior, right? With inductors, if you don't know what an inductor is, maybe not. It's like the magnetic-y version of a capacitor. But with capacitors and inductors together, you get complex numbers in your circuits. Or to analyze them properly, you need to use complex numbers. We won't do that. But I want you to understand that capacitors in their steady state, easy, breezy, beautiful, cover girl. But capacitors in their non-steady state, complicated, scary. Okay, what about two capacitors? Let's say I have two capacitors. One of them is big. One of them is small. And they're connected in parallel, okay? Like this. So they're both plugged into the battery in the exact same way. I want to ask you, which of the two capacitors, I'll go freeze the frame. There we go. Which of the two capacitors has the higher voltage? Echo pole. The big capacitor, the small capacitor, they're the same, or you can't tell. One of them's small, one of them's big. So I'll give you a hint. The small capacitor and the big capacitor are not the same thing. They're not the same capacitor. One of them is bigger than the other. That has to mean something, right? Right? Well, actually, no. They have the same voltage. They have to have the same voltage. We just learned in that double red slide 2 slides ago, 3 slides ago, some slides ago, that when two things are plugged in parallel, they have to have the same voltage. That's the rule. It has to be that way. But big capacitor, bigger than small capacitor, right? So, I know, right? Mind-blowing. So the question becomes, what's different about them, right? If they achieve the same voltage, what can we say is different about them? Well, obviously, yes, that capacitance, but we don't know what that is yet, right? So I want you to think to me, which of these two is going to have more charge on it for the given voltage? The big one or the small one? The big one probably has more charge. Imagine, take this capacitor, it has a charge of Q. Cut it in half. Probably has a charge of Q over 2, right? That's how that works. So, the big capacitor has more charge, and the small capacitor has less charge. And as someone correctly points out, we should have a way of referring to that. We should have a way of expressing how much charge can you shove on this thing for a given amount of voltage. How much charge does this thing have the capacity to store? What's it called? Capacitance. This is my own ears tour. All right. Where's the next slide? There. Capacitance. This is what capacitance is. It's charge per voltage. Because when you connect two capacitors to a battery, they will always have the same voltage. So voltage isn't the unit, the item we need to be concerned with. It is the capacitance. Okay? So this hopefully makes sense for us. If we have two capacitors, one of them is big and one of them is small, they will have the same voltage. But the big capacitor has a bigger charge, and therefore the big capacitor has a bigger capacitance, because capacitance and charge are linked. Okay? Now C is the capacitor in farads, Q is the charge stored, and V is the voltage across both sides. Now what this means is that a given capacitor can store however much charge you can put on it, provided you've got enough voltage, right? A big capacitor and a small capacitor, you could technically charge them to the same level of charge. You just need to use a lot higher voltage for the small capacitor. That's what this is saying, okay? Now, one other thing to keep in mind is, I left my watch in my office. That's a very important thing to keep in mind, because I can't check the time now. I have to look at my phone. What? Oh, I took it off. I appreciate you. Why am I so stupid? Gosh. So I have to rush out on time because I have to go buy an important book for our Women in Physics Trivia Challenge next week that you all saw the announcement for on Moodle, right? And you all saw the announcement about the barbecue this Friday that I organized, and you're going to come support me in the football team. We got owned last year. We got not American football. Don't worry, it's touch Australian football. No, it's not Australian football either. It's rugby, the worst football. Don't at me. I played rugby as a kid. It sucks. And we're going to get wrecked, all right? We got absolutely wrecked last time because we played the UNSW official touch football team, and they absolutely rolled us. And we're going to get rolled again, and I roped in the director of teaching to come in. So he's playing. He's my PhD supervisor, and he's going to be there. So come watch. And also free food. Everyone's poor, likes free food. Where to put my watch? Over here. Good. So, the capacitance of a capacitor, sorry for my little ramble, right, is the amount of charge across the capacitor. And I'll notice, right, when you have a capacitor charged with a charge of Q, as we would say, then the positive charge is Q and the negative charge is negative Q. It's not Q over 2 on either side, it's Q, right? So I know Q there is the charge stored, right? That's referring to this charge and that charge. That's the number we use. Okay, now the reason we do this, we'll see a little later, right? But the reason we refer to it like this is because that's how we referred to two parallel plates when, heavy hint, we were doing electric fields. Remember, we had a charge of Q, we had a charge of minus Q, and we figured out the electric field between two parallel plates, or two cylinders, or two spheres. Maybe those all show up somewhere. But yes. So that's the definition of capacitance. And another thing I'll emphasize to you is that you can get... No, I'll emphasize it to you later. There's too many things. I'll do it later. All right. Let's try an example question. Now, who forgot a calculator again? Me, of course. Slay besties. Anyone can lend me their TI-82? Don't. It's okay. This is Texas Instruments. It's a calculator that Americans have, right? Besties, you know what a TI-82 is, right? Yeah? See, what is it? I know. It's an American thing, right? Anyway, a capacitor has 10 microfarads. Oh! What's the unit for capacitance? Someone should have told you that. Me. It's farads. Oh, great. Yeah, there we go. It's in farads. What's the letter for farads? F. Yeah. So keep in mind, Q has to be in coulombs, voltage has to be in volts, and then you get capacitor in farads, F. Okay? A 1 farad capacitor is insanely huge. Like, if you have a 1 farad capacitor, that's, doomsday level capacitor, all right? We deal with microfarads, we deal with nanofarads. So let's take an example. We've got a capacitor, it's got 10 microfarads of charge on it, and a voltage, it's got 10 microfarads of capacitance, and we charge it with 12 volts. How much charge is stored on each plate? Well, C equals Q over V, and then you just rearrange it. We do a lot of this. We do a lot of rearranging, okay? So we're looking for Q. So Q is equal to CV. Wow. That was pretty easy. So that's, I didn't screw that up, did I? No. Okay. 10 times 10 to the power of minus 6. Very good. Times 12. And that becomes 1.2 times 10 to the negative 4? Is it 4? Yeah. Good. What unit? Coulombs. So here's a problem, all right? The symbol for capacitance is the C. The unit for charge is C. The symbol for voltage is V, and the unit for voltage is V. All right? There's a lot of repeat letters. There's only 26 of them, and for some reason they keep naming them after people. All right? So volts named after someone, coulombs named after someone, farads named after someone. I'm sorry. We should have had people with cooler names, like Greek names or something. I tell you what, if everyone gave their names in Mandarin and they had to use the Hanzi, we'd never have repeat units, right? There's a lot of characters there. All right. So I mentioned at the start of today that actually, maybe, wink, it is very useful for us to derive the capacitance of various shapes. All right? Because there's only a few common shapes you're ever going to deal with. And what I want you to realize is that it's the same shapes. We're always using these shapes. It's always two parallel plates, the goats here, right? Then two cylinders, like this one. That's a cylinder inside a cylinder. It's got a stick just so I can hold it, okay? So that's two cylinders, right? So this is a capacitor as well. And then theoretically two spheres. It's kind of a bit interesting. How would you charge the inner sphere how do you get at it? But whatever. We're not thinking about that. We're theorists right now. And so you have to be able to derive the capacitance of the following shapes. And you might think, oh no, Tom, is it time to do another integral? And the answer is, of course it's time to do another integral. But it's the same integral you've done like 50 times, okay? We do literally the exact same thing we've done when we tried to find the electric field between these two objects. And we do the same thing we've done when we tried to find the voltage between these two objects. It's the same, except now you add an additional step of C equals Q over V. So basically what we're going to do, right? Don't worry, I always got you. I write a strategy steps page, don't worry. Assume that there's a charge of plus Q and minus Q. Now, maybe the question will give you little q instead of big Q, or maybe the question will do Q over 2, or whatever. You know, assume that one plate has the positive charge, the other has the negative charge. It doesn't matter which one, because when you do capacitance, more technically, it's like that. It's technically the absolute value of the potential difference between the two plates. The direction doesn't matter, right? We treat the capacitance as almost the scalar on a scalar. We're not really considering if you got a negative or a positive. Just whack a positive on it. Okay, so we assume a charge of plus or minus Q. We use Gauss's law to gain an expression for the electric field between the two plates. And I want to take a moment to appreciate all of you now are probably seeing Gauss's law as routine, which is, you know, a pretty great learning gain considering how, 2 weeks ago, I introduced Gauss's law and we all shat ourselves. So like, you know, you're growing up. We're learning, which is pretty good. Then we use V as the integral of E dot ds, which we did last week too, right? But maybe you're a little less comfortable with this. This one was hard. If you watched the live stream of the problem-solving workshop that I did late last night, God, that last question, that was the absolute worst question I've seen in my entire life. I hated it. Every time I saw it on the question list, I was like, I'm not going to practice that one. And then that came back to bite me in the ass. And then we just do this. Step 4 is the only thing you've not done before. Everything else you've already done for several other questions, right? In fact, beneficially, you might even remember some of the answers, right? Because it doesn't change. The voltage between two parallel plates is still going to be, hang on, it's V equals, what was it? Q over epsilon naught A times D, right? I just remember that. The one for two cylinders, I think it's Q over I don't know, 2 pi RL epsilon naught D or something? I don't know. But you remember the vague shape it takes, right? You do enough of these and you actually start to remember them, which is kind of nice. Like, this is what it means to be a physicist. You're like, oh, it's this again. Oh, I can do this, right? It's kind of knowledge construction. So what we're going to do for, I believe, the next half of an entire hour is just practice 2 of these derivations, right? Seriously, it's getting kind of easy from here, right? Now that we can do Gauss's law, we've got heaps of time. So what we'll do is we'll go through the entire lesson as always, right? And I'll do more demonstrations because I'm finally, for once, experiencing what it's like to actually have time in lecture. And then we'll do round robin questions to help you prepare for the exam, right? If you've got exam questions, or like, you know, those of you who did your exam, I'm sorry, right? But you get to relax. You have a fun time today, right? All right. So we got parallel plates like these. Before we begin with any derivation, you should be able to guess or have an expectation on the answer. So these 2 plates. Do you think bigger plates or smaller plates has bigger capacitance? Bigger plates. That would make sense, right? Bigger plates, bigger capacitor, hopefully. So we're expecting to have Q. We're expecting to have a working computer. The fact that the live stream crashed halfway through and I lost the entire recording, I am just cursed when it comes to computer. All right, so we're expecting C is going to be somewhat proportional to, let's say, the area of the plates, so the surface area of the plates. Do we think or do we know, closer together or further apart, what gives you more capacitance? Ooh, any guesses? Closer together, maybe? Is it further apart, maybe? I don't remember. So we're going to derive it. I think it's the opposite of whatever A is, which means that a smaller D means more capacitance, right? If I remember correctly. I just remember it being the other way around. What about charge? What about Q? How should Q relate to our capacitance? It shouldn't. A capacitor has its capacitance regardless of how much it is charged, regardless of whether or not it's charged. It's a property of the thing, the object. It's like how the area of this plate is always the area of this plate, no matter what you're doing with it. It still has that area. And capacitance is the same sort of thing. It shouldn't have an expression of Q in there at the end, okay? That's one thing you have to get out. We're going to do this expression, and Q should come out because it's supposed to be a material property. Now, if I recall correctly, it's going to be epsilon naught A on D, right? If I recall correctly, but let's derive it and see if I remember, right? Let's see. So we're going to find the capacitance. Step 1 is to find the electric field, right? I'll go back one slide just so we have the method up at the same time, okay? Freeze image. Okay. Is it up? Yes. Oh, whatever. I was going to say, should I move it that side? But, like, people over there, can you see that? Yeah? Okay, good. Okay, good. So, step 1 was, to put a charge of plus or minus Q on the edges. We already did that, right? Goated. Nice. So, step 2 is to... I am becoming the Joker. All right. Step 2. Yay. Step 2 is to use Gauss's law to get an expression for the electric field. Now, I'm going to do this a long way just because maybe you'd like that revision, all right? So what we do is... What? Why? Why does this happen to me? All right. What we do... Okay, 3rd time's the charm. What we do is, we draw a Gaussian cylinder. Remember, it's like a Gaussian pill box, right? Now, in the olden days, it was a snuff box, but we don't do that no more, and I don't know what that is, because I'm not that old. And we draw this little cylinder, and, okay. No? Why does computer hate me? That's the question I should put on Echo Poll. Why does computer hate Tom? Anyway, we'll go back. So what I'm trying to do is change the color. And it seems like every time I try that, it shits itself. The electric field from the positive plate is radiating out this way and this way, right? It's radiating out in the vertical directions or like away from the plate. So in this case, it'd be out this way and out that way. So the area that is experiencing some flux is only the two ends of the cylinder. So the total area that is experiencing flux is twice pi r squared, right? Where r is the radius of our cylinder. So this is r, okay? Now, because I introduced r, I pulled it out of my arse, it has to go back in there. That was a horrible statement. Because I made up this variable, it has to go away, okay? Oh, that one's... Sorry. All right, so because I made up that r, it has to go away. That's what I mean to say, all right? So that's the area in this one and this one. And we know that the electric field times the area is equal to the charge enclosed over epsilon naught. Now, the electric field, this is only true because we've drawn ourselves a Gaussian surface for which the electric field is constant and goes directly through the surface. All right? Nowhere else. Are you texting someone? Don't post it to the Discord, please. Good. There used to be someone who would post all the weird shit I'd say to the Discord, and I'd die every week, all right? Yes. Anyway, so we've got this, right? And again, you know, we get to do E times A because we made a good Gaussian surface. See the Gaussian surface lecture that we had earlier. And so now we have, well, the charge enclosed here, right? The charge enclosed here must be equal to sigma, the charge density, multiplied by some area. And the area is the area of one of these circles. So it's sigma times pi r squared. Okay? Now, I notice I'm bringing in a lot of variables here, right? We haven't defined sigma, but they've told us that the plates have an area of A. So we say, well, sigma is equal to the total charge divided by the total area. And then this finally gives us that E times 2 pi r, and I notice this A and this A are not the same. I'm a bad person. I should have. So we'll call this A of the Gaussian surface, just to distinguish it from A, the area of the plates. The electric field times the area of our Gaussian surface is equal to, in this case, Q divided by the area of the plates times pi r squared. We do some cancelling. We remember epsilon naught, because I'm not a stupid dumbass. And then we get E is equal to Q over A 2A epsilon naught. There's a 2 there that I didn't uncancel. All right? So to revise it again, we've got E times the area of the Gaussian surface is equal to the enclosed charge over epsilon naught. The Gaussian surface area is 2 pi r squared. The charge enclosed is going to be Q over A, the charge density, times pi r squared, the size of the circle, that the size of the circle of the plate that we're enclosing, divided by epsilon naught, and you get E equals Q over 2A epsilon naught as your electric field due to the first plate. And due to the second plate, you get the exact same value, right? This second plate, we could repeat the process again, right? We could draw another Gaussian surface, and we would realize that this plate is negative, so the electric field goes in, right? Now, this was in the pre-lab for this week's lab, so hopefully you've all done this before, right? The electric field goes in, so in this case, the electric field is, and we do this exact same maths, and we get Q over 2A epsilon naught. This is acting down. I don't know. This is acting down. Oh, it wrote this time. Okay, this is acting down, and this is acting down. Right? So cumulatively, E is the E due to the negative plate plus the E due to the positive plate. Wow. And so E is equal to Q over A epsilon naught, which is a definition we've used so many times. The electric field between two parallel plates is that. We just know it. And so now, taking that parallel plate, and this is why I put 2 copies of the slide on here, we have a line for no reason. E is equal to, I'm getting angry. I shouldn't get angry at the physics. I already forgot it. Q over A epsilon naught. Yeah, that was up. That's what's up. Right? Q over A epsilon naught. That was our electric field. That's step 2. We did it. We got the electric field. Now, we'd already done that a bunch of times before. I just did it slowly this time for revision. But we'd done it in a couple of other lectures. Now it's time to determine the voltage between the 2 plates. Now, the best part about using capacitance is if you get the direction wrong, screw it, whatever. Just absolute value that voltage. It's fine. We don't need to worry about the direction this time. All right? The best kind of answer. So, V, technically delta V, is equal to the integral, negative, of E dot ds, and S is going to be like that. Right? That's our S direction. It's going from this positive plate to this negative plate. What? Oh my God. Why does it go, it never goes consistently either. I bet you there's a button on this pen, and I've just got fat ass fingers. I would never be an embroiderer. Anyway, so because E is constant, right, it's going to be equal to negative E integral ds, which is literally just negative E ds, S, right, where S is the total distance traveled, right? We could say, okay, well, this is between 0 and D if you want to. And then that would give us, well, actually, that derivation is negative E times D, the distance. Right? Remember, we said these parallel plates have a distance of D. So the voltage between the 2 parallel plates is equal to E times D, or Q over A epsilon naught times D. That's step 3. Now again, we've done this before. We found the voltage between the 2 plates. I got rid of the minus sign because whatever. Who gives a crap? It's capacitance. You don't need the minus sign. All right? But if we were to be correct, we would define, well, technically S equals 0 is here. Why does it do that? Why does it do that? Yeah, I agree, bestie. That book slam, that's me. That's my vibe. This is technically S equals 0, and this is technically S equals D if you want to get really funky with it, but like, whatever. We're looking for the voltage between the whole 2 things. Doesn't really matter. And so now we finally go, okay, C equals Q over V, which is equal to Q over A epsilon naught D, which becomes A epsilon naught on D. That's the capacitance of 2 parallel plates. Pog. We did it. Thug life. Wow. Do you reckon you could do that in an exam? No? Oh. Okay. Maybe become the kind of person that could do that in the exam. That's my... Sorry? Oh, no. The next exam. Yes, you should be able to do everything up until that Q over V part for the first exam, if I'm honest. However, I think it's kind of crappy that they're asking you to do Gauss's law a week after learning what Gauss's law was. That it took me ages to understand how to do Gauss's law, but once I got it, I have it forever. It's like riding a bicycle or doing a domain expansion, but I'm not going to tempt fate and invoke Jujutsu Kaisen again. Not what after happened last time. Alrighty. Now let's try 2 cylinders. We'll go back. So it turns out it does kind of depend on the way we think it depends on things. Right? It doesn't depend on Q, like we thought. It does depend on A, like we thought. And it is inversely proportional to D, like some smart people over here thought. So you put them closer together, they have a high capacitance. How interesting. How odd. Wonder how that happens. Maybe it's got something to do with the fact that the charges are attracted to each other the closer they are or something. Who knows? Who knows? Do I know? No. That's what the math says. Just believe. Smooth brain our way to victory. Okay, let's do 2 cylinders. Are we going to do the exact same problem? Yeah, that's what we'll do. We want to find the capacitance of these 2 cylinders. Our first intent, our first point. Excellent. That was me going back and forth just to make sure it was on the right slide. Right? Our first point is step 1. Anyone remember step 1? Put the charges on. Technically, step 1 was put the charges on. Do we want the middle charge to be positive or negative? Positive. Hell yeah, let's go. Q. And this one's minus Q. Hell yeah. All right, nice work. Alrighty. Number 2. What's the second law? Or what's the second move? Gaussian surface, right? Rogi Tenkai. I shouldn't have said that. That's like an anime thing. It's not like a bad word. We're going to make a Gaussian surface because we need to find the electric field between these 2 cylinders. All right? So what we're going to do is we're going to imagine first of all that I can draw a circle. Okay? That's the first thing you need to imagine. And the second thing we're going to imagine is we make our own Gaussian cylinder. All right? Our Gaussian cylinder has a radius of r. Okay? And, oh, I forgot I wrote the derivations down. Oh, excellent. I was like, oh, Tom, you better not screw this up live, but it turns out I have the answers. Our Gaussian cylinder has a radius of r. Okay? And we're again going to go, well, E times the area of the Gaussian surface is equal to the charge enclosed in the Gaussian surface divided by epsilon naught. Now, what we're going to assume is that our Gaussian surface, which is a cylinder, I'm drawing it on its side this time, is exactly as long as the cylinder that we're dealing with. Okay? Now, we could do it assuming a subset of the cylinder, but I'm just lazy. We're just going to assume it's equally as long. Okay? That way we have the whole charge enclosed. We don't have to do any like charge density bullcrap. Speaking of bullcrap, yeah. Oh no, it worked that time. Okay, I'm sorry, computer. I'm sorry. That's the length L, right? Like me, that's what I take all the time when I'm trying to use computer. God. All right. I was reading this article about how it was Gen Z, you're not good with the computer, but like, no, I'm not good with the computer. All right? Anyway, we have our cylinder, it's length L. So now we need to compute all these terms. The area of our Gaussian, I just genuinely don't get it. All right. I'm not touching any of the buttons. They're here. Anyway, the area of the Gaussian surface, we only care about the rectangle part, right? The part that wraps around the inner cylinder, because that's the part that the electric field is going through. And of course, we assume that it's perfectly perpendicular and that the electric field is constant to it at all times. Again, we assume we did a good job in picking our Gaussian surface. And so the area of that cylinder is 2 pi RL. Yeah, 2 pi RL, right? 2 pi R, that's the circumference of a circle, then L, the length. So that is the area of this section of the Gaussian surface. Okay? Now the charge enclosed, that's just big Q. It's just big Q. Right? That's all. Because we don't need like to do any density stuff. We just enclose the entire charge. So this means that E is equal to big Q over 2 pi R L epsilon naught. Done. Right? Now, of course, this is technically only valid for R between the inner and the outer radius. Right? But, you know, whatever. So that was step 2. Find the electric field. Again, hopefully, you should already have to do that. People who already did the exam, did you have to do that? Yeah, some people are nodding. All right, good. Those of you who are about to say no, hold your tongue. And say no. You have to say it like us. N-A-U-R-R, or however we say it, apparently. All right. So, no. And well, let me go back. All right, so now we have, we'll use yellow again, Thug Life. Oh, maybe we'll try green. How's green? Do we like green? All right, it's more pleasant looking than yellow, isn't it? It's very, very good. All right, so E, I already forgot it, was equal to Q over 2 pi R L epsilon naught. Was that it? All right, gangster. So now we need to find the voltage between these 2 points, right? We need to find the voltage between here and here. And what we're going to do is we're going to integrate our electric field along this distance, right? So we're going to say, well, the voltage between the 2 points, delta V, is equal to the integral, negative, of E dot D. Forgive me for going dr, because we know it's just moving along the radial direction, right? We're not going to bother with ds equals dr, but it's moving along the radial direction. And importantly, the limits on this integral are from the inner cylinder, and I'll use big R to differentiate it from the variable r, from the radius of the inner cylinder to the radius of the outer cylinder. Oh, it's my hand. It detects my hand. The whole time, it never had hand rejection. It just thought I was touching it with my hand. Oh, this is a game changer. Yeah, it thinks I'm clicking when I touch it. Ah, I'm such a boomer. Anyway, we're doing this integral, right? And so that's the integral equals minus, but we know we don't care about that minus. It's going to go away anyway, right? The integral of Q over 2 pi R L epsilon naught. Gosh, it's much harder to do this. dr between big R and R plus D. And so we'll take all the stuff at the front that is constant. So that's going to be delta V is equal to Q over, well, technically minus Q over 2 pi R L. There's no R there. You never saw that. That never happened. There's no R. Integral 1 over R dr between big R and R plus D. What's integral of 1 on R? Graphing calculator besties. You don't know? Log. Well, ln, we'll go ln, right? Log base E, right? I know you mean log base E when you see log, but some people mean log base 10 when they say log. It's pretty crazy. So that's equal to minus Q over 2 pi L epsilon naught, so far so good, logarithm of R plus D minus logarithm of R, right? Wow, that's a lot. So then that's equal to negative Q, I'm going to write it up the top here, negative Q over 2 pi R L logarithm of R plus D over R, right? That's the voltage between those two. Now, that again, that was in the lab this week. You had to be able to derive it to get full marks, so hopefully you did, because you've all done the lab, because it was yesterday, right? And you had, that was part of the job, was to derive that. All right. And then we just upside down it. That's all we got to do. C is equal to, okay, divide by Q, right? And we get rid of the minus sign. So, okay, so there's more than one step. I'm sorry, right? But it's conceptually quite simple. There's no integrals. C is equal to Q over V, which is equal to this stuff upside down. 2 pi, that's an epsilon naught. No one saw it being an R. That was an epsilon naught the whole time. 2 pi epsilon naught L over logarithm R plus D R. Now, the customary check that I did that correct. Yes. Good. Right? Now, the only thing to keep in mind, oh, you want me to write it out bigger, like the actual answer? No? Okay. The only thing to keep in mind is that sometimes they'll give you R1 and R2 instead of R plus D and R, right? But that's our answer. Again, it doesn't depend on Q. It depends weirdly on the distance, right? But it depends obviously on the length of the cylinders. The bigger the cylinder, the bigger the capacitor in lengthwise. And then with the radiuses, it's more so about the difference in radii between the two. And you could do some computation on that if you want, but I don't want to. Okay. And that's actually the first half of the lesson. That's it. We actually did every example for once in our lives. So we'll take like a 5-10 minute break, all right? Sphere is left as an exercise to the reader, all right? How do you do sphere? You do the exact same thing we did. The electric field due to a sphere, it's some integral on r squared. No, the electric field has a 1 on r squared component. It has to, because it's the electric field. It's just regular arse electric field, right? It's 1 over 4 pi. It's q over 4 pi epsilon naught r squared, right? We remember that, or kq on r squared. And then you'd integrate that. So you'd integrate r squared, or 1 over r squared. Integrating 1 over r squared gives you what? 1 on r. So it's just a 1 on r relationship. It's pretty chill. You should be able to do it, I believe. All right, now we have a break. Those of you who did the test, enjoy the stress of those of us that have not done the test. My favorite thing about doing a test is having done it. And then you go, I don't have to do the test. But also, don't be stressed out about it. Physics is not real life. I would like you all to do well. We're getting emails where people are like, Tom, give me more marks. And the correct way to email that is Tom and Kate, give me more marks, please. Because Kate is the actual boss. Kate's more important. No, she doesn't like when I do that, but she is more important. You know, Kate's the actual goat. I am just her messenger. And welcome to my cult. So did anyone who went to the live stream last night? 1, 2, 3, 4, 5 of you. Yay! It was interesting. How's everyone else's other life going? Anyone doing anything fun with their lives? No, why not?
You're studying for physics.
You're studying. Oh, I didn't study when I was your age, and look how I turned out. So you better study. That's kind of lame. I don't know. You're here to achieve a life for yourselves, not to study. Spend all your life studying. Especially those of you who are here on exchange, right? Like you're here to do dumb shit, right? You're here to get pissed drunk on beaches. You're not here to do anything else, right? I assume. All right. Exchange students, why did you pick here?
They offer good classes.
Okay, I like this one. Wow, thank you. Also, Yanks, why did you pick here? Change scenery. What about you, Bestie?
I was gonna go to Europe, but then I realized I can't handle the cold.
Can't handle the cold. Well, you came to the right spot. Who's excited for 40 fucking degrees tomorrow? We're gonna. Nah, you're going to get sunburned. You're gonna get skin cancer. See, notice the difference in our faces of all these spots that I have. This is what happens when someone of our complexion lives in this country. It's a mistake. My entire family, like my mom's had skin cancer removal 7 times. No, you have to understand that's normal here. People just like, oh yeah, I'm just going to get my moles cut off again. Just happens. Unironically, right? Yeah, see? Pointing at like the person who I assume has been sunburned before in their life.
My dad's a redhead, and his whole family are redheads.
Tough life. Has anyone transfer students have gone to the beach yet? Yeah?
They're right before I came here.
Yeah! Oh, sick. Which one? Coogee?
Yeah.
Dog shit beach. Terrible beach.
What's your favorite beach?
My favorite beach. Shit, good question. Okay, don't laugh at me, but I really like North Bondi, if I'm honest. I don't like the South End because the waves are too big and they're scary. But the North End is nice. It's very shallow, very chill. The northern beaches are nice, but I won't say anything. The best beaches are obviously in Western Australia. Like that's.
See the sunset over there?
Yeah, that's what Powderfinger sing about. It's dad rock band. Powderfinger. You gotta listen. Sorry?
Good song.
It is. I love it. It's unironically one of my favorite songs. I'm old. I'm out. What else we got? We got chilling. Bottle of water. No, that's British. Has anyone been to England? It's cold. Wait, oh, you're from fucking Wisconsin. It's normal.
And then winter and summer.
Yeah. Did you bring any pants or just shorts?
No problem.
Wow.
I had to wear them.
Yeah, you wouldn't. You wouldn't. Hello. Oh no, it's just some guy. Never mind. Who is excited for the course to be over so you don't have to do exam anymore? Yeah. Right. Who? I haven't even looked at the content for next week. I should probably write those lectures at some point. But that'll be done. We'll get it done. I usually write them over the weekend. So, and now my girlfriend's in London right now, so I don't have anything else to do for her. She's going on an art gallery tour. Yeah. But she's just loaded. Not like from her own business. She runs an art business, and so she just had big money. She's like, man, let me go overseas now. So she's seeing art exhibitions in London, a bunch of other ones in the UK, and then Florence. She's just gone, just cause. And I'm slumming it here, like a loser. All right, what do we think? Do we think the Normie mic is back? Please, Normie mic. No, it's still low battery. All right, I'll let it charge some more. Okay, so we'll try some demonstrations because they'll be fun. So earlier we had this capacitor, right? Now we're going to do a different capacitor. We'll get rid of this. We'll get rid of this one. We'll take this one. I'm going to charge this cylindrical doodad, okay? So this goes over here. This goes over here. Okay. So here's hoping I don't damage myself. All right, we'll give this a try. Turn it on. Cool. Cool. Okay. All right, so it's charging, and this is forming a capacitor, right? These two. So you can't see its capacitance because there's no like indication of electric field. But what's happening, and I'll try and remove, I don't have enough hands. So all right, and I'll try and take this out. The idea is that this, oh, we're good. This has some charge on it, and that has the opposite charge on it. And the idea is that only when I connect them electrically together does the charge discharge. So I'm going to try and see if I can. Oh, hang on. Go? No? Okay, hang on, let's try this again. Yeah, I broke it. Oh. It made a tiny little, it made the smallest sound ever. All right, so basically this is a capacitor. Is it? Yeah, it's a capacitor. What I'm primarily, oh, it smells really bad. Ew. Okay, anyway, there's this thing in the middle. This thingy, right? So we've got this outer cylinder, put the thing in, and then we got this inner cylinder. Does anyone want to take a guess? What's the purpose of the thingy? Insulator. Why would we want an insulator in between the two plates? Oh yeah, first of all, so that they don't touch. But does the property of this insulator carry any relevance? I want you to think about that. Does the property of this insulator, presuming of course that it's an insulator, it's not going to be a conductor, right? But does the property of that insulator have any bearing on the capacitance of this capacitor? That's what we're going to learn today. Because the second lesson is step 1, explain how a capacitor changes when you add another charged plate in it. And this is what I thought that question I was struggling on last night was asking us, right? And then we're going to talk about how a capacitor charges when you add a dielectric to it, which is just an insulator. But dielectric has a specific word. I know, new words. And then we're going to talk about the energy stored by a capacitor. And it's honestly not that bad. So, what happened here? Right? First of all, where pen? Oh, here pen. Yay. Okay. So we got a parallel plate capacitor, like the olden days. There's a charge on the top, there's a charge on the bottom. They have a constant electric field between them. And let's imagine we have some initially uncharged conductor placed inside this electric field. I want you to tell me exactly what's going to happen to that conductor inside the electric field. Something starts with P. Rhymes with polarized. Polarized, going to be polarized, right? So what's going to happen is we're going to have a bunch of positive charges down here. Almost screwed that one up. Lamau. A bunch of negative charges in here. Okay. Now, of course, these positive and these negative charges are not at all connected to the actual positive and the actual negative charges. And if we had this, connected to a voltage source, right, connected to a battery, that conductor is not connected to the battery. But it changes the capacitance. And it changes the capacitance in a way, I want you to think now that capacitance is storing energy. That is somewhat true, and we will learn the mathematics of it later. But what I want you to think is, if I added this conductor, does that allow it to store more energy? Does that provide more energy storage options? Or does that provide less energy storage options? Because what this conductor does, is it either, and it is one of them, but I haven't told you yet, increases the capacitance or decreases the capacitance. And when I guessed wrong. So I want you to just think, all right? Don't call it out. What we're going to do is figure out if the capacitance got bigger or smaller, all right? And what we want to do is find the capacitance of this new capacitor and compare it to the capacitance before we added the plate. This shows up in some form of assessment. Maybe I looked at all the questions and wrote the exam slides, but wrote the slides based on it. Who knows? That's a theory. I totally don't look at the exam questions to figure out what I should teach you. Well, look, are we going to derive the capacitance of this parallel plate capacitor again? No, it's the same thing. We did it before. We find the electric field, it's Q over epsilon naught A. We find the voltage, that's just that multiplied by D. And we find the capacitance, which is just upside down of the voltage, and then get rid of Q. We already did that. We did that like 30 minutes ago. So that's that, right? Now, what will happen when we add a conductor? Well, first things question, and it's echo poll time, right? Get on your phones, besties. It's time for TikTok. If you remember, it's echopoll.au, and then the code is physicsgang. There we go. What's the electric field in there? I'll give you a hint. It's one of those three options. What's the electric field inside the conductor? Keeping in mind that the electric field here and the electric field here. Oh, sorry, I went to the next slide because I touched it with my hand. Repole. Yeah, it's open again. Don't worry, it's open again. Keeping in mind the electric field here is Q over epsilon naught A, and please forgive the fact that I wrote E, because if you write epsilon, the echo pole shits itself. All right? So I'm not doing that. All right, what do we think? What do we think? What do we think? We wait. It's 0. Now, the reason it's 0 is because we learned that in a slide. One thing I want you to do a lot of in this case is sometimes you'll be like, I feel like something should be happening here, but there's a law that tells me that actually this incredibly simple thing must be happening. And generally, the law that tells you to think less is correct. It's a conductor, there's no electric field in it. That's always true. Doesn't matter what circumstance it is. Doesn't matter that there's any other interesting stuff going on, we don't care. All right? It's a conductor, there's no electric field in it, end of discussion, go to your room. Right? That's the kind of, it's like you're a parent. That was the analogy. Not that I'm a parent. You are all my children. No. Well then, how does it change the capacitance, right? Because I just said that it changes the capacitance, and if the electric field inside it is 0, well, then what are we doing? Well, it changes the way we do our integral. Because remember, our integral from the top to the bottom was assuming that the electric field was constant the whole way. I really tried to not trigger this stupid thing. There we go. We assumed that the electric field was constant the whole way, and if there's a capacitor in it, it's no longer constant the whole way. It's constant down to here, then it's 0, then it's constant down to here. Now, we could, if we have time, derive that the electric field in these two portions is the same as though there was no extra conductor, all right? I can derive that for you if you want, if we have time. We're not gonna unless we have time, but take my word for it, right? The actual answer is, of course, because, well, any negative and positive charge contributions will cancel each other out because the electric field due to a plate is constant with distance. So via the law of superposition, they just cancel each other out. You don't have to worry about it, right? Or you could just do, okay, Gauss's law, charge enclosed is 0 because there's a positive side and a negative side, right? Either way, the important thing is that the actual conductor only has 0 electric field in it. It doesn't change the electric field anywhere else, okay? The electric field here is still E equals Q over epsilon naught A, and it's still that over here too, Q over epsilon naught A. So all we really have to do is do a voltage integral that's slightly more complicated. It's not really an integral, right? It's not really an integral. So that's what we're going to do. We're going to derive that the new capacitance is the old capacitance times this divided by this doodad. And this doodad is necessarily less than 1, and therefore the capacitance is increased, which is not what I thought would happen, right? But it is. It's like, I guess because by polarizing the metal, it's storing more energy. That's the way I think about it, right? There's energy stored in that polarization. That's the only way it makes sense to me. But, yes, question or alternative explanation. Yes, and so that's what confuses me, right? Uh-huh. Yes. Yes. Because there's a slow, I get what you mean. So we're having that. Yeah. And so this functions as a functional decrease in distance because we've got 2 capacitors with a smaller distance instead of 1 capacitor with a bigger one. That's a very good way of thinking about it. Nice work. I'm going to accept that as my headcanon. Thank you. Right? Very good. It's always so satisfying when people can explain physics for me. Anyway, so now we got to derive it, right? And it's actually big easy. The voltage between these two plates, because that's what we're going to try and find. We're going to find the voltage between the two plates, then we're going to take Q over it, and that's what we'll get, right? Is equal to, well, first of all, I need to give you another distance. So I'm going to make up a letter. What letter should I make up? Give me a letter. A. All right, nice work, everyone. This distance is A now. A now. You're a rock star. No. Sorry. You guys know Shrek, right? Yeah? Do you know Shrek is older than you? Yeah. Yeah. No, on God, for real, no cap. 2003, Shrek. Yeah. Your mother was born on Shrek? You're as old as Shrek, okay. I remember seeing Shrek in the cinemas as a child, because I'm 32. Anyway, so this is going to be the negative of, but remember, we don't really care about that negative. The integral of, let's go between, let's call it x. Let's decide that this distance is x. It doesn't really matter what distance. Oh, let's do s, fine. S equals 0 to s equals a of E dot ds plus 0. So the second stage here, this is 0. And then the third stage is the negative of the integral from s equals this distance here, a plus b, to s equals d, this distance here. So we're integrating it in 3 steps. We're going from here to here. Then we're going from here to here, which is 0, so we just ignore it. Then we're going from here to here. And because I've introduced this letter a, it has to go away later. So sorry, this is integral e dot ds. I really should have specified, shouldn't I? Right? And we recall that e was equal to q over a epsilon naught. So let's do that integral. This is equal to negative, but we're going to make it positive anyway because we don't really care, right? Q over a epsilon naught of s between 0 and a, right? That's that integral, plus 0, plus negative q over a epsilon naught s between a plus b and, sorry, a plus, yes, it is a plus b, and d. And now let's just solve that whole thing. So this is equal to minus q on a epsilon naught a plus 0 minus q over a epsilon naught a plus b. Sorry, d. That's how integrals go. It's the top one minus the bottom one. I'm a dumbass, right? Minus minus. I knew this because I'm waiting for the a's to cancel out, right? That's how I knew I did the plus wrong. Minus minus q over a epsilon naught a plus b, right? Sorry about the integral minus sign wrong. If I had progressed with it the wrong way around, we would have realized the a's don't cancel, and I would have immediately realized I'd screwed up because the variable I have invented has not gone away, right? And the way to succeed in this course is, well, the way to not screw up in this course is just to get really good at realizing, ooh, no, right? You want to have a good spidey sense. Okay, so that's going to be equal to minus q over a epsilon naught with a on it, plus q over a epsilon naught with an a on it, minus q over a epsilon naught with a d, and then plus q over a epsilon naught with a b. All right? And then those a's cancel out, and we get to figure out how to use the eraser. Eraser. It is customary to make the sound when you use the eraser. Right? Pen now, good. So the voltage is equal to q over a epsilon naught negative qd plus q over a epsilon naught b, right? Which is just q over a epsilon naught b minus d. Now technically it should be d minus b because I've used the sign the wrong way, right? But we'll figure that out when we get there, right? Because yeah, I'm just gonna write d minus b. Maybe this was the one where I actually had to do the minus sign correctly instead of just deciding it doesn't matter. My apologies, everyone. All right, Lamau. Anyway, and then we go, well, okay, the capacitance therefore is this over q, so we get a epsilon naught over d minus b, and then that's the new capacitance. The old capacitance was a epsilon naught over d, and then so we take this one and we take d out the front, we go a epsilon naught over d outside of 1 over 1 minus b on d. I know it's kind of a bit all over the place. And then this was capacitor old, right? This is C old. So then we find this. That was anticlimactic. I know. Please tell me that's a face of like, oh yeah, I get it, instead of like, what the fuck are you doing here, man? All right. So what do? Basically, we just did the voltage integral in increments, right? We did the voltage from one part to another part, and then we did 0, and then we did the voltage from the second part to the third part, right? I'll show you again as a laser pointer. We do the voltage from here to here, then we add to it the voltage from here to here, which is 0, then we add the voltage from here to here. And because we have slightly different limits on our integrals, which I've already deleted, I'm very sorry, we get a slightly different answer for capacitance, all right? I'd recommend doing the derivation at home with actual paying attention to signs instead of just me winging it, right? Recommendation, do that. do what I am too lazy to do. But unfortunately, we must move on and do some new things. So what that means from a vibes perspective is clearly to get more capacitance, you just put more conductors in it, right? So if I wanted to make this parallel plate capacitor have more capacitance, I could just fill it with conductor. What's a potential drawback to that? Yeah, if I fill the entire thing, well, it was a question, but let's just say you're correct, right? If I fill the entire thing with conductor, then all of a sudden, the end's short. They're just connected via a wire, and then it's not a capacitor anymore. So somehow, we want to fill this thing with conductor, but not actually fill it with conductor. And so the question becomes, what was the property of the conductor that was good, that helped us with the capacitance? It was the ability for it to become polarized. Because it was when the electric field within it was zero that we got an increase in our capacitance. So allow me to introduce something called dielectric. A dielectric is an insulator that is still polarizable. So the charges cannot move, but, well, then maybe they can move just a little bit, right? It can't conduct current, but it can have polarized charges. I really should have put this as a double red. This is more important, right? And this allows them to store energy via becoming polarized, positive, but they don't short out the capacitor, negative. So basically, it's what we pull in our capacitors. And that's the answer to, did the material of the plastic matter? Well, kind of, right? We would care about what we would call the dielectric constant of this object, which is kind of how good it is at storing energy. Dielectric constant. This shows up a lot. Now, when I was doing my research for these slides, what I really like is that it was the phrase referred to in old textbooks as the dielectric constant, but correctly apparently referred to as the relative permittivity, right? So that tells you what kind of textbook we were working off, right? It is some constant that tells you how the permittivity of this object is different from epsilon naught. Basically, this object, and technically all substances, have their own epsilon, right? Just like how substances have their own refractive index or have their own magnetic permeability, right? This has its own epsilon that's not epsilon naught. Epsilon naught is the epsilon of air, or of free space technically, but air is close enough to it, right? And when you put in, this is the easiest thing in the world, when you replace the air with a dielectric constant, with a dielectric, you replace epsilon naught with epsilon of the dielectric, and that's the only thing that changes. That's it. All you do is you take epsilon naught out, and you put epsilon in. Or even lazier, if K is the ratio of epsilon to epsilon naught, then any system where you replace the air with a dielectric of dielectric constant K, like for example, let's say we had the capacitance of a regular capacitor, which was A epsilon naught over D. That's the capacitor if it's full of air. If it's full of a capacitor, if it's full of a material with a dielectric constant kappa, then the capacitance of the new material, or the new object, is just kappa. You just multiply kappa in there. Because all you do, whenever you have a new material, you only replace epsilon naught. That's it. Dielectrics are the easiest shit in the world. Until you see the questions you're going to have to do. You have my condolences for next week. By next week, I mean on Friday. The opening slide on Friday is, the questions are jank. I will prepare you for them. So that's all you do, right? If an electrical object is filled with a dielectric instead of air, you just use the new epsilon, which is equal to kappa times the old epsilon, where kappa is the dielectric constant, epsilon is the electric permittivity. They might give you one or the other. They always give you kappa in this course, I think. That's all you do. That's the only difference. Everything else is identical, unless, of course, the dielectric is only in part of the capacitor. Oh, no. Oh, no. But we'll deal with that next week, okay? We're doing that on Friday. We're dealing with it on Friday, okay? For now, it's either all or nothing, okay? So that's literally it. You've got a capacitor with a dielectric in it, you just put kappa on it. That's all. It's the easiest shit ever, all right? So what that means, by the way, is that the addition of a dielectric increases the capacitance, which was the whole point of putting a dielectric in, right? Because remember, the dielectric, it lets you store energy by polarizing the molecules or whatever other chemistry's going on, I don't know, but polarizing it, right? It stores a little bit of energy in the material. And so you're like, yay, more capacitance, because I can store more energy in it like this. And if I were to take out the dielectric, it would be a slightly shittier capacitor. And also, obviously, I'd like short it all the time. But it would be a slightly shittier capacitor. Slay. So this is really easy. Dielectrics are easy when they're filling up the entire capacitor. I want you to think, what's the capacitance if it only fills up half the capacitor? The answer is suffering. Okay, what if I ask you to find a formula for the capacitance as a function of how far the dielectric's gone in? That's an actual question you might see. I'm going to teach you how to solve it. Don't worry. Don't worry. It's not today. Today, we rest. Okay, today we chill. The other thing that shows up inexplicably somewhere is this thing called with dielectric strength. So I want you to imagine these two parallel plates are separated by a material. And you can imagine at some insanely high voltage, the dielectric's going to short out. Right? At some stupidly gigantic voltage, current's going to go through the dielectric anyway. Right? And this is what we call the dielectric strength. It's technically the maximum possible electric field that a dielectric can sustain. Because inside a dielectric, right, it's little charges moving a little bit. They're kind of spinning on their axis or something to align with an electric field. And if the electric field is really, really strong, those charges will just straight up move, right? They'll just straight up break their bonds or do whatever, right? Something Magneto? I don't know. I don't watch X-Men. So if you exceed this, well, usually it blows up, right? That's how you can blow up dielectric capacitors, is you overcome their maximum possible electric field. Air doesn't have that. Air can do it forever, right? So you don't have to worry about air, right? Okay, well, air will technically spark at some point. We saw that in Jacob's ladder and all this other stuff. But relatively speaking, it's not too bad. So that's where the dielectric strength comes in, all right? That's the maximum electric field. So if you can figure out the electric field in a parallel plate capacitor, which you can, then if they tell you the dielectric strength and they ask you how close can these two plates be together before they break, you can figure that out. Okay? Wink. Hint. Who knows? Okay. Now it's time for our final concept in our final half hour together today. How many slides did I put on this? Only 6. Nice. So we're almost done. We're almost done, and then we can relax. Well, those of us who finish our exam, we can relax. You can go to the beach. You did your exam already? I knew all the 1, 2, 2, 1 students must be transfers because no one does 1, 2, 2, 1 these days. All the cool kids do 1, 2, 3, 1. But I think your university is going to accept 1, 2, 2, 1, right? You sure? Good. That's good life then. That's good life. Wait, are you also an American? Nodding person? Oh. Slay, sorry. Sly, I don't know. Yeah, nice. 1, 2, 2, 1's easier. I would do it if I could. All right. So now, we're going to do our last thing. Oh, I wrote Tom Freeze here. Thank you, future Tom. No, past Tom. Yeah, that's how time works. Okay. So, energy. All right. What we want to do now is derive the total energy that can be stored in a capacitor. Okay? And you might think, oh, Tom, well, it's just the total charge times the total voltage, right? Because energy equals QV. No, it's not that. For once, something different. How interesting. How are we going to figure it out? Of course we're going to integrate. Of course we're going to integrate. Okay? I love integrals. I want you to imagine that you're charging a capacitor. Actually, I'm going to unfreeze frame. Future Tom, you really dogged me. All right. When you're charging a capacitor, right? And in the transient form of this capacitor, like when you just plug it in, or when it's plugged in a little, or when it's about to be finished, there's an element of charge dq that the battery is trying to put on the plates. And the question I want to ask you is, at which point, right, during the charging cycle, is the energy required to move that charge, let's call it du, the greatest? So what's going to happen is, as the capacitor charges, initially there's no charge on here, right? And then sometime later, you know, there's a little bit of charge. And then sometime later, there's a lot of charge, right? And I want you to think, does the amount of energy, du, required to move this amount of charge, dq, onto those plates, does that change over the process of charging this capacitor? And if it does, where during the charging process does it take the most energy to put just a little bit more charge on those capacitors? I've really emphasized or hinted at the answer here. Sorry? You're guessing? Which letter do you guess? It's one of them. It's either A, B, C, or D. That's my hint to you. So, okay, the whole point is guessing, right? You haven't done this before. All right, so where does it take the most energy? It is a diverse set of questions. I like that. I like that. I actually had a fair amount. So it is at the end of the charging. Okay? It's at the end of the charging, but let me explain why. So we'll go back. Right? Let's explain it in two ways. Let's explain it in two different ways. Okay? I wonder if I can add my own. No, I don't think I can. All right. Oh, I would like to draw, please. Okay, now I want load the pen. Load the pen. Give me the eraser. Okay. So, the first way of thinking about it is that when you're taking this charge, this element of charge, which we'll call a positive element of charge, right? If you are putting it on a neutral plate, that's fine. It doesn't really care. You're like, yeah, sure. All right, put it on the neutral plate. If you are putting this element of charge on a plate that is already massively positive, you have to push it there. It won't go there by itself. It's trying to repel away. And the more positive that plate gets, the more you have to push to put the damn extra charge on. As you add more and more and more charge to this distribution, it becomes more and more and more energy intensive to add more charge. And we can think of it another way. We can say, well, let's imagine the charge between these two capacitors is some voltage V1. Right? The voltage between those two capacitors is some voltage V1, and we could work out using C what that voltage is, right? To add an element of charge to that voltage separation, you have to give it the amount of energy V times dq. You have to give it that much energy in order to get it to go to a voltage separation of that much. All right, V1. Right? And this is actually why charging stops when the voltages are equal. Because when the voltage across these two parallel plates is equal to the voltage of the battery no longer has enough force to put more charge on the capacitor. It can't do it anymore because the capacitor is just as charged, it is just as voltagey as the battery. The battery has no more push than the capacitor. In fact, they're pushing almost an equal amount against each other, right? The positive charge here, if you tried to make it go along this way, it would experience exactly as much force pushing it back from this positive charges here than it would experience by the battery pushing it forward. And the only way to get more charge onto that capacitor is to increase the voltage of the battery, to push harder. And that's how you would stack more charge on it. And so if we're thinking, what's the cumulative amount of energy that we would have to have added to charge this capacitor? It depends on the charging process. So all we can define for now is the work done to add an increment of charge. The work done to add a little bit more charge to a capacitor, which we'll call dW. It's going to be integrated. Oh my God, no way! Is dQ, that's the little bit of charge we want to add, times V, where V is the voltage at that time. At that point, V here is a variable, because depending on how much voltage is between the plates, that affects how much energy it takes to put a little bit more charge on. Because if they're already really saturated with charge, it's really hard to put more charge on it. So du, which we could say is the change in energy of the capacitor, because we're trying to find the total energy of the capacitor. The amount of energy added to the capacitor is the charge added to the capacitor, dQ, times the voltage at that time. And the problem is, as you add more charge, the voltage goes up. So V is not constant. V is a function of Q. It's actually VQ dQ. Right? V is not constant for a capacitor that is in the middle of being charged. And so if we want to find the total energy of the capacitor, we need to integrate it. Right? So this is what we're going to do. Maybe this is something you'll have to do. Right? We have this, and you can take my word for it that it's true. Whenever you see those red slides, the red border boxes, you can just assume that it's true. All right? I'd like you to be able to understand why it is true, but it took me a solid few minutes at a tea store to figure that out. Nice tea store, by the way. If any of you live in Ashfield, go to Moment Tea. They gotta have more customers so I can continue going there. Right? They're goated. It's very good. So, we'll substitute V equals Q over C, where here we're using little q, because what I'm saying is voltage here, V, that's the voltage at whatever point in time we're talking about. And Q is the charge at whatever time we're talking about. So it's not the final charge, it's not the final voltage. It's the voltage at some time and the charge at that same time. Okay? So as I said before, voltage is supposed to be a function of Q. And so in this case, it's Q over C. Luckily for us, let's just assume capacitance is defined. We don't have to do that weird earlier definition. But we do know that if you charge a capacitor to half the voltage you charged it before, you'll have half the charge, right? So that relationship V equals Q over C is true because of the definition of capacitance, right? C. I figured out what's happening. It's because how I write is I rest my hand down first and then bring the pen in. And I've got to do it at the same time. Okay, here we go. Yeah. I have to do like that weird thing. Anyway, we know C was equal to Q over V, right? And we just rearranged that to solve for V. That's what we did. V equals Q over C. That's all we did. Okay. We know how to rearrange. I know, unbelievable. So, then we arrive at this infinitesimal. Okay, we have this. du, the amount of energy added to a capacitor when you add a little bit of charge to it, is, no! Come on! I hate technology so much. Is equal to Q over C. I know, same, bestie, same, right? Times dQ. Whatever, it's this doodad. Now, what do we do to find the total energy? We're going to integrate it. We integrate it from charge equals 0 to charge equals final charge, big Q. And you get this. The total energy stored in a capacitor is a half Q squared over C. Okay? Now, you can use this integral to answer questions like, how much energy is added over the second half of the charging when the Q is half to the Q is full, or over the first half of charging? Those two won't be the same, right? Integral from 0 to Q over 2 versus integral from Q over 2 to Q, not the same, okay? Because it's got Q squared in it. And because we have C equals Q over V, all of these are alternate forms, okay? Because you can make substitutions however you want. So it's half QV. It's not QV. Isn't that interesting, right? Or half CV squared. Wow. How exciting. Maybe, maybe not. Who knows? And this is our final note. We actually finished the lesson early for once in our lives. Nice work, everyone. We slayed today. The final expression is charging from 0 to full, okay? And that final expression, that's the one that you see a lot. That's the one that you use a lot. But we take it for granted, right? Half QV or half, what was it, Q squared on C, or half the other one, I forget, right? That is only the total energy. It's the total energy added over the entire charging process. If you get asked about a subset of the charging process, like from when it is half of its voltage to when it is full voltage or something like that, you have to do the integral over that subset, okay? You can't just do it. You have to do, well, actually, you don't have to do the integral. You can just make substitutions, but please keep that in mind. And that's the whole lecture. You did it. Yay. So now we have an extra 10 minutes. Is this Friday a public holiday? What? Yeah. Yeah, it better not be this Friday. Yeah. One of my staff members just asked, do we have class this Friday? I'm like, yes, right? You still have to work, right? I would, no, wait, is next Friday a public holiday? It can't be. I'm giving my lecture. No, my last ever lecture, are you sure? Are you dead ass on God? For real, no cap? Let's check this now. Sydney, what's it called? Public holiday. When's our next public holiday, besties? 29th. Oh, yeah, no. That's ages away. That's heaps away. Oh, excellent, good. I would, if I didn't have to do part of my job, oh, I don't know what I'd do with myself. All right, well, now we have like 10 whole minutes. You can do what you want. You can go, you can ask questions that I'll answer about tests and stuff. If you've got your test coming up, maybe you want to ask questions about that. If you don't have your test coming up, maybe you just want to go take a nap. Go to the beach. Go to the beach tomorrow. It's good beach weather. It is. It's going to be 40 degrees. Coogee Beach I don't like because it just slopes really hard, right? And I'm short. So I can go like 10 centimeters into the water and I'm just drowning, right? It's hard. No? Okay. Well, early mark then. We did it early. Nice work, everyone. Bye-bye. That actually works for me because then I have to rush off anyway.